Hey, welcome back. Now we're doing cylindrical and spherical coordinates. So it's another way of doing a coordinate system. Cylindrical is just an extension of the polar coordinate system. So that should be relatively painless to introduce. Cylindrical, and this is connected to polar. So first, let's remind you of how the polar graph system works. So here we are sort of imposed on the xy plane, and we can specify any point in this plane given a directed angle and a directed distance. So let's say we have this angle in this direction, theta. The length of this arm, I guess, is r. We can designate this point with r comma theta. The connection to then the rectangular system we could find via trig. So note that that we're dealing with a right triangle here. So if you have cosine of theta, that'll equal adjacent, which is the x coordinate, over r. In other words, or rather x is equal to r cosine theta. And then you could say sine of theta is equal to opposite, which is y all over r. So we have y equaling r sine theta. This is a right triangle, so you have Pythagorean Theorem that tells you that the sum of the legs squared is equal to the hypotenuse squared, so you get x squared plus y squared is r squared. And then finally, there's a tan formula as well. So tan of theta equals opposite over adjacent. Okay, so it's basically those equations. Now we just add on a third element that would be the z variable. So let's take a look at it in the xyz plane. So in the xy plane, it's basically business as usual. You have this point here, which is, again, described via this angle theta and this directed distance r. But then you have a third dimension, which it will be z. Right, so you'll have this point here, which is r comma theta comma z. Okay, so this distance is z, and all the equations are the same basically. So this is my z-axis. So this over here is polar coordinates, and then this picture over here is cylindrical. So again, you have x equals r cosine theta, y equals r sine theta, and then z is just z. Okay. Tan of theta is y over x, and of course we have x squared plus y squared equals r squared. Okay. The first kind of problems you'll see in the homework over here to the right will be converting coordinates from cylindrical to rectangular and then vice versa. So first, let's look at going from cylindrical into rectangular. You can always kind of just do a small sketch to make sure you're on the right track if you want. In the xy plane, 3 comma pi over 4, here's pi over 4, and then you're going out 3 units on that arm, so you should be in the first quadrant. So that's sometimes a helpful guide. But anyways, to get into the rectangular, the z is the same. Z is z, so we just put 1 there. X is equal to 3 cosine pi over 4. So cosine of pi over 4 is root 2 over 2. So obviously we get 3 root 2 over 2. The y coordinate is 3 sine of pi over 4, so that'll be the same, right? So it'll just be 3 root 2 over 2. Okay. And that would be it. Okay, let's look at going in the reverse direction, so from like rectangular to cylindrical, rectangular to to cylindrical. Okay, so these are examples. The numbers don't really matter. I took them from the book a long time ago, and the numbers have changed over the years. So anyways, again, it's a good idea to figure out which quadrant you're in, especially for going from rectangular to cylindrical. You need to know kind of your angle. So you need to know which quadrant you're in. Here, I should be in the first quadrant. 1 radical 3 is somewhere in here. So anyways, in this orientation, you need to use the tan formula, the tan of theta. Tan of theta equals, and again, the z coordinate will just stay the same. But anyways, tan of theta equals y all over x. So in this case, theta, so we are radical 3, so that would be pi over 3 for our theta. So you get, then you need the r value, so r squared is equal to x squared plus y squared, so that'd be 1 plus 3. So r squared is equal to 4. We want the positive r, so plus or minus 2, but we'll take 2, right? So 2 pi over 3, comma 4 would be our answer. So maybe any of these homework problems we want to do. These all seem kind of simple. Let me try, oh, that's, no, this, let me try number 4 from the book and see how that works. So we're going from 7, -7, 2 into cylindrical. So again, we could just copy down the z coordinate, but we're going to be in which quadrant? So the 4th quadrant, already then. If they need a positive, so if they need your theta to be in between 0 and 2 pi, the calculator won't give you that answer. The calculator will give you an answer between negative pi over 2 and pi over 2. So you just basically have to add accordingly to get it into the right quadrant. But for that, you need then the reference angle, and then you take 2 pi, subtracted the reference angle, and that should give you the appropriate answer. But anyways, let's look at this one. So we have tan of theta equals opposite over adjacent, so -7 over 7 y over x, which of course tan of theta is going to give me -1. Normally, if you put that in your calculator, you're going to get negative pi over 4. If you need it in between 0 and 2 pi, then you just, this is the calculator answer, so you just get the reference angle, which in this case would be pi over 4. And then for the official theta, you would take 2 pi minus the pi over 4. And of course, that would give you the 7 pi over 4. But I bet the computer will take either answer. I'm not sure, but I bet. I didn't even try. So anyways, x squared plus y squared, it gives me my r squared. So I got 49 plus 49 equals r squared. In other words, r squared is 98. So r is plus or minus square root 98. I need the positive r, so I got square root 98, then 7 pi over 4, and then 2. Okay, once you wrap your brain around that, you're going to want to be converting the equations from cylindrical to rectangular and vice versa. So just doing coordinates is the first step. Now we want to deal with equations. Okay, so equations, and first we'll go from rectangular to cylindrical. For the rectangular form, you're usually looking at some function, hopefully an x, y, and z. For cylindrical, you're hoping to get r equals some function of theta and z. Okay? It's not always possible, though, so you may end up with some sort of implicit form. Fortunately, the computer is pretty good about this. Usually, if you can't solve it for r, I wouldn't even bother and just leave it as r squared. And you can see in problem 5 over there, that's kind of what I did. Let's go ahead and look at problem 5. So they give you an equation in rectangular form, and you want to convert it into cylindrical. So the quickest way is just to get rid of the x and the y. And you could use your conversion formulas from up here to do that. So it's these formulas you're applying. Okay? In particular, x squared plus y squared is equal to r squared. So I can automatically just replace the x squared plus y squared with r squared minus 6. And the computer is good with that answer. You can literally just put that in and it's happy. Okay. So if you need to, for example, do the equation of an ellipsoid, x squared plus y squared plus z squared equals whatever, you could literally just replace the x squared plus y squared with r squared plus z squared equals 9, and that would work. Okay, that would be your answer. Let's look at another one. So see number 6, that one on the right here, that one is, so blatantly idiotic. The equation is the same in cylindrical and in rectangular coordinates. Sadly, number 7 there is not so simple. Let's look at that guy. So y is x squared. So I'm going to replace y with r sine theta. Replace x squared with r cosine theta squared. So we get r sine theta equals r squared cosine squared theta. And in this case, I'm going to try to solve for r. You'll technically, when you divide both sides by r, you're losing a solution. You're losing r equals 0. But it turns out that your answer will still have that encoded. Okay, so anyways, first I want to divide both sides by r and then flip sides, so I get r cosine squared equals sine theta. Then I'm going to divide both sides by cosine squared, so I get r equals sine theta times 1 over cosine squared is secant theta, so secant squared theta. Then I should be kind of good. It seems, so long as you're not worried about, I'm looking at my answer. Yeah, and you see my answer is not the same, but I bet they would accept this answer. So how did I get the answer that I put in for number 7? Well, I just rewrote sine theta times 1 all over cosine squared theta. You could rearrange things a little bit and get sine theta all over cosine theta times 1 over cosine theta, and that gives you the tan theta times secant theta that you see in my answer. But I'm pretty sure that the computer is good with either answer. And again, like I was saying, you think maybe in this step, when you divided by r, you lost r equals 0, but that's not true, because if you let theta equal 0 down here, so when theta equals 0, then you have r equals tan of 0, which is 0, times secant of 0, which is 1. But 1 times 0, of course, is 0. So you still get r equals 0 in your solution. I don't think that you should take that as kind of like, oh, I can kind of finagle the reasoning behind any answer. What I'm kind of taking the bullet point of the book there, the main point idea is not to get too carried away with your final answer. Just kind of, look the other way. You could divide by things. Don't worry about division by 0 in this context, is kind of what they're saying. Okay, so ultimately you're hoping to get an explicit r equals something in terms of theta and z. It might not always be possible, and sometimes it's not even warranted. You probably don't even want r equals something. So especially here, you would end up with a plus or minus square root thing. You don't want that. So just leave it, and this is called an explicit form. So explicit means that you have y equals like some function of x and z or something like that, some version of that. We usually can't get that, right? So an implicit form would be more like the equation of a circle, where you have x squared plus y squared plus z squared, or in this case, an ellipsoid equals 1. Okay, so again, it's not always favorable to solve for r, but sometimes that's if you can do it, go ahead and do it, and don't worry about dividing by 0. Okay, so hopefully that makes some sense. Let's see some more examples. Let's say they have the equation in cylindrical form now, and you want to go in the other direction to rectangular. Okay, so cylindrical to rectangular, so part D, I guess. D equations, cylindrical to rectangular. Okay, so again, think about your set of equations that you have. X is r cosine theta, y is r sine theta, x squared plus y squared is r squared, tan of theta is x over y over x, and then z is z. In this case, it's this equation that's going to allow us to get rid of the theta and put us in the x and y and z. So tan of theta is pi over 6, so tan of pi over 6 equals y over x. Okay, tan of pi over 6 is just going to give you 1 over root 3. So what do you get? You get an equation of a line, right? So you can solve for y equals x over root 3. And in this context, because we're in space, it's the equation of a plane, right? So you could probably kind of draw it in space here, x, y, z. The trace in the x, y plane, you have a slope of 1 over root 3, so it's going like this through this, and then it's kind of connecting. It's a plane like this. Okay. Hopefully that's reasonably well. No, it's getting worse. Okay, well there it is. R equals 2. So looking at the homework problem over there, number 9, they just give you R is equal to 2. So for this case, it's this formula at the top. X squared plus y squared is r squared. So you can just replace r squared with 2. And of course, that's one of our cylinders. So in the xy plane, we get a circle with radius 2. And then you could just extend that into the z direction, and you get a nice cylinder object. Okay. So yeah, you can see got it drawn there. Then yeah, theta. For some reason this was hard to figure out which picture they were looking at, but sort of got there after a while. R squared plus z squared equals 4. Yeah, that's just a sphere. Another cylindrical. So r equals 4 sine theta. Let's try that one. Okay, so for example, r equals 4 sine theta. Note that x squared plus y squared is equal to r squared, and not only that, we can kind of connect it to the formula y equals r sine theta. Okay, so note, you may have to play around with these a little bit and spin your wheels in order to get the formula, but after a while, there's only so many variations on the theme, you know, and you're going to be able to figure out which is which. But here, you can rewrite y using this formula for r. So y is 4 sine theta times sine theta. And then you could say, well, that's equal to 4 sine squared theta. Okay, so watch what happens when I plug r in here. So I have x squared plus y squared equals 16 sine squared theta. Okay, that 16 sine squared theta is an awful lot like 4 sine squared theta. So if you write x squared plus y squared equals 4 times 4 sine squared theta, you've not changed anything, but you can do a substitution, right? Because y is equal to this 4 sine squared theta. So you end up with x squared plus y squared equals 4 times y. And then you could move the 4y over and complete the square. Okay, so plus blank equals 0 plus blank, right? So negative 4 over 2 is negative 2. Negative 2 squared is 4. Add that to both sides. So you get x squared plus y minus 2 squared equals 4. And lo and behold, you have a circle centered at 0, 2, with radius 2. Okay, so it looks like this. And in the XYZ plane, then, you're out here. Before you have this circle, and then you could just extend it in the z direction, and you got your picture, right? So it's like an off-center cylinder. And so it's, yeah, this first one here with radius 2. That's pretty much the same thing, but with a 7 cosines theta instead of sine theta. You got cosine theta, so you have an x on the other side. Okay, so once you wrap your brain around those, we get to something that is a bit different, spherical coordinates. But you can kind of leech off the polar coordinates again in order to produce the spherical coordinates. Okay. Spherical coordinates are good when you're dealing with spheres. Cylindrical coordinates are good when you're dealing with cylinders. Okay, the equation for a cylinder is pretty simple. The equation for a sphere in spherical coordinates is pretty simple. So anyways, there's some restrictions on our variables that I should note. Rho is greater than or equal to 0, and r is greater than or equal to 0. Okay, that's my Greek letter phi. This is my Greek letter rho, and then r. Okay, so the deal is this time in the xy plane, you could still kind of, so this is my x, this is my y, this is my z. In the xy plane, you could still kind of think about theta and r, okay? So theta is here and r is here, but we're not going to use theta. The thing that we're going to use is phi, which will be kind of, you're dropping down away from the z-axis, okay? So this will be the angle we're worried about, and then ultimately our point will be at the end of this arm, and its length is rho. If you want to, you can drop a perpendicular down there so you have a right triangle to deal with. This coordinate will be given in terms of rho, theta, and then phi. So yeah, we are using theta, sorry. Okay, so I need the conversion formulas. You can kind of get your hands on them just by first using this triangle down in the xy plane and using polar coordinates. So in the xy plane there, I know that what do we have? So x is equal to r cosine theta, and y is equal to r sine theta. See, we want to put the r though, and we want to get rid of the r, right? So I note what r is equal to in terms of phi. So first off, from geometry, there's some alternate interior angles here. This angle will end up being phi. If you take the z-axis and then this dashed line here as being parallel, you have phi alternating interior angles. So those two are the same. So then you could say that maybe before we solve for rho, we'll say that the so sine of phi will equal opposite. So thinking of the opposite from this angle phi, that'll be r all over hypotenuse, which is rho. So you could solve out for r as rho sine phi, and then rewrite x and y in terms of rho and theta, and rho and phi, sorry, so this would be phi. Okay, so x will equal what? R, which is rho sine phi, and then cosine theta. And then y we could rewrite as rho sine phi sine theta. From there, we can get a formula for z. So this distance here, this vertical distance is z. So I note that the cosine of phi will equal adjacent over hypotenuse, where rho is the hypotenuse. And then you can solve for z as rho cosine phi. We can say that tan of theta, as usual, is equal to y over x. Pythagorean Theorem type stuff, using, I guess, this blue triangle right here. We have r squared plus z squared is rho squared. So we have r squared plus z squared is rho squared. And then you just replace r squared with x squared plus y squared. So we get x squared plus y squared plus z squared equals rho squared. What else can we do? From this cosine phi formula here, we can get another relationship. So we could say cosine of phi is equal to z all over rho. From this formula, if you solve for rho, you get rho, because rho is greater than 0, the square root of x squared plus y squared plus z squared. And sometimes that formula is helpful as well. Okay, so you get a ton of formulas. You basically use these things to convert the coordinates and the equations like we did with the polar coordinates. Okay. Okay, so let's, hopefully that wasn't too rambling. Let me just dive in there then and, kind of do these conversions. I typically won't put spherical type conversions on the test because I expect you to kind of have to look up those formulas, but cylindrical definitely you should be able to do on a test, because I'm assuming you did polar stuff in Calc 2, and that's just one extra variable. So anyways, right, let's try it now. Converting spherical coordinates. So here we go. So the first one, coordinates going from spherical, no, rectangular to spherical. Okay, so they're giving me the point -9, root 2. Keep in mind all the restrictions on your variables. Anyways, let's take a look. So rho is going to be, actually, how are we going to do this? So this is x, y, z. And then this guy is our rho theta phi. And I want to convert. Looking at my notes for where, did I do any of these in my notes? I don't think I did. Anyways, we had one of these. Okay, so it's one of these. Actually, I did the other way around, didn't I? They gave you, no, this is rectangular to spherical. Okay, we're good. Right, so rho is going to be, the square of rho is going to be x squared, so 81 plus 81 plus the square root of 2 squared is 2. So 162 plus 2 is 164. So this is 164, right? I don't trust myself anymore. So rho will be the square root of that thing, whatever the heck that is. Square root of 164. For theta, you could just do the tan of theta equals -9 over -9, which would be 1. So take theta to be pi over 4. Make sure that's in the right region. They don't give any restrictions on theta. You just usually make that between 0 and 2 pi. And then phi, you could use the cosine phi formula. So cosine of phi is equal to rho z over rho. So z is root 2 all over rho. We figured to be something nasty. Square root 164. Ugh. So 41. Anyways, I'm going to have to go and do cosine inverse of that thing. And I bet because it's not a nice answer, you could probably just type it in like that. I don't know why I didn't. Okay, so it looks like we got square root of 164, comma, oops, comma, pi over 4, comma, cosine inverse. Let's see if they allow us to put it in like that. Cosine inverse of square root of 2 all over square root of 1. For some reason it gave me a square root 164. See if it likes that. It's probably going to be ticked about it. Yeah, I'm seeing an X. The only thing, oh, I see what's wrong. I'm in the wrong quadrant. All right, so if you think about the x, y, and then -9, -9, -9, you're over here. So this theta answer's wrong. So you need to be at what, 1, 2, 3, 4, 5 pi over 4, and then that should do it. Drum roll. Yeah, see. So they're pretty nice about the form that you put your answers in. If they're not looking for, if they don't say, you know, a decimal approximation, usually you just put cosine inverse of the thing in there and it's happy. And okay, so that's rectangular to spherical. Let's try the other way around. Spherical to rectangular. Spherical to rectangular. This time I'll be a little more careful, make sure I'm in the right quadrant and stuff. But anyways, I guess looking at like number 17 there, we have 7 pi. This should be a little less painful. Pi over 2. So this is rho, theta, and phi. So, you know, tan of, well, I don't think we want to go on that way. So, how are we going to do this? So cosine of phi, we want to use that one. So we could just use our x and y formulas to get x and y. So rho sine phi, cosine phi. So x is rho sine of phi, cosine of theta. Y will be rho sine phi, sine of theta. So we get those pretty easily. X is sine of pi over 2 is 1. Cosine of pi is -1. Sine of pi is 0, so that one's 0. So you get -7, 0. And then for your z coordinate, it looks like we can just use rho cosine phi. So z is rho cosine of phi, and that will be 7 times 0, which is 0. So that direction is fairly painless. Okay. Finally, then we're working with equations. So part C now. Equations. We'll start by going from rectangular to spherical, and do something easy. So like the example we have, that y equals 3, which is number 18. Let's make this the video quiz for the day. I'll make sure it's in my notes. This is the last video quiz. This should be video quiz set number 2, so you should have 11.5, 11.6, and 11.7 in it. There's no video quizzes in the review videos, but anyways, let me write this down in my notes. So this is actually problem number 18 from WebAssign. y equals 3, and we want to go from spherical, no, we want to go from rectangular to spherical. Okay. Very simply, just get rid of the y, and we want everything in terms of rows, phis, and thetas. We have the formula for y above. It's rho sine phi sine theta equals 3. Typically, they want you to get it in terms of rho equals something. So just like before, you wanted rho equals some function of theta, you wanted r as some function of theta and z. Now we want usually rho as some function of phi and theta. Ideally, okay, that would be the explicit form, but sometimes just leaving it in the implicit form with like a rho squared or something is not going to be a big deal. Okay, so anyways, in this problem, to get rho equals, you just divide both sides by sine. And of course, 1 over sine is just cosecant, so you get 3 cosecant phi cosecant theta. Okay, so that's the video quiz question. Let's look at some more examples. So here we got x squared plus y squared equals 16. And we can replace x squared and y squared with the, rho sine phi cosine theta. So for x, it's going to be rho squared sine squared phi cosine squared theta plus y will be rho squared sine squared phi sine squared theta, and then equals 16. You could factor out the rho squared sine squared phi. Whoops, rho squared sine squared phi, and you just have the cosine squared theta plus sine squared theta, which is equal to 1, equals 16. And so you could just rewrite this as rho squared sine squared phi equals 16. And then you could take the square root on both sides. And I usually don't like to do that, but you can do that. You can get sine, rho sine phi equals 4. Divide by sine phi, and you get this nice explicit formula. Well, like I said, the software is pretty allowing. If you wrote this, I'm sure the software would probably take it. But if you want rho equals, you got to do this. So 16 cosecant phi would probably be kind of the official answer. Okay, and yeah. Okay, let's look at another one like this one here. If you see my answer on the right for number 19, that's not even correct. You should more or less follow kind of what they did in the book. It seems like I was just throwing stuff at a wall and seeing what stuck. So for this problem, you want to approach it more like this one. So this is example 5, I guess. They're looking for the equation of a cone. And you see how they go through this, and then they do the square root and get plus or minus. It'll turn out in the software, you don't need to list the plus and minus. You could just put phi equals whatever. And so let's look at this problem. And my answer, you see, it's way off base, but they still gave me credit. It's just crazy. Anyways, let's take a look at this thing. And I'll kind of try to do it the way the book does, okay? And you'll see. Well, actually, let's do a similar. Practice another version, so it'll be similar. They give us some crazy number, 80. Okay, great. So the way the book does it is replace x squared plus y squared with our rho sine phis, cosine theta type stuff. So you get rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. Then you could factor it out and simplify it. On the right-hand side, you'll have 80. Then instead of writing z, I'm going to replace it like they do in the book with rho cosine phi. Right? So you end up with 80 rho squared sine squared, actually cosine squared phi, right? Because that's how we defined z. Then you're going to, again, like I said, factor out the rho squared sine squared phi, and you just have the cosine squared theta plus sine squared theta, which will be 1. On the other side, you got 80 rho squared cosine squared phi. All right, so you end up with rho squared sine squared phi equals 80 rho squared cosine squared phi. You're going to divide out by the rho squared. It'll turn out that doesn't really matter. That won't hurt you. So you get sine squared phi equals 80 cosine squared phi. Then you're going to divide both sides by cosine squared. And so sine squared over cosine squared, of course, is tan squared phi equals 80. And then you're going to take the square root on both sides, but just don't even worry about the plus or minus issue. Just put square root of 80. And then take tan inverse on both sides. So you get theta, or phi equals tan inverse of the square root of 80. And then that should be good enough for your answer here. In the book, they could actually find the inverse of phi. So you see they get 2 answers, and one is basically one part of the graph and the other one's the other part of the graph. But in the software, they're not going to bully you into giving both answers. So you just write one of your answers in. And in particular, in this case, tan inverse of square root 80, that's not well known. So you just write write it literally. So anyways, I need a Greek letter phi. So hit the phi and then equals, I need a trig for tan inverse the square root of 80. And hopefully that'll do it. I don't know if there are any tricks about it or what. Yeah, there we go. Okay. Okay. I think that's really kind of the worst of it. Let's work with going in kind of the opposite direction then, going from spherical into rectangular. So part D, equation, spherical and the rectangular. So the first problem you see to the right there in web assigned number 21 is pretty simple. They have rho is 6, so we know that rho squared is equal to x squared plus y squared plus z squared. Rho is greater than 0, so you could just plop 6. I guess it doesn't matter that rho needs to be greater than 0. You can plop 6 in for rho. You get 36 is x squared plus y squared plus z squared. And of course, that's just a sphere with radius 6. So let's see another one. Another example. Theta is pi over 4. Well, that's just, we have a nice one, conversion formula. Tan of theta is y over x. So plugging in pi over 4 for theta, you get 1 equals y over x. In other words, y just equals x. So that's just going to be a plane going through the line y equals x. This line here. And then you can kind of control the plane. Yeah. All right, well, there's that. Yeah. There's only one plane to choose. It's that one. So there it is. Phi equals pi over 6. So another example. Phi equals pi over 6. I think you're probably going to have to go to that phi formula we produced. Right with this guy. And then you'll be able to get it into x, y, and z. So cosine of phi equaled cosine of phi, which in this case is pi over 6, equals z all over the square root of all that x squared plus y squared plus z squared. So, as you go through these, ideally you have the list of formulas in front of you, and you're just using those to convert. Okay, so cosine of pi over 6, of course, is 1/2. So we get z all over this junk, squared plus y squared plus z squared. I'd square both sides, so you get 1/4 is z squared all over x squared plus y squared plus z squared. And it looks like you're going to get kind of an ellipsoid type deal. You can cross multiply. Well, maybe not, right? So this is x squared plus y squared minus 3z squared is 0. You may have to do some trace analysis to figure out what you're dealing with. So in the xy plane, you just are getting a point, but if you push out in the z direction, you'll get ellipses. So originally it's just a point, but if you push out, you're going to get some ellipses. So it seems like it's probably going to be a cone, elliptic cone. But let's make sure, right? So in the yz plane, you get y squared minus 3z squared is 0, so you get y squared is 3z squared, and it's starting to look a lot like a cone, elliptic cone. And then xz, yeah, you're just going to get another. So it's going to be like a double-headed cone in the xy plane. Let's see, we got a point here, and then it's going to go out like that, and then down like that. Okay. So, yeah. That equation you could just multiply to get my equation. Multiply through by 4/3. Or okay, so it's not a double-headed cone. Z is greater than or equal to 0. Okay, so that means it's just the top half of the cone. What else? Why is my answer different? Why is my answer different? Cosine of pi over 6 is 1/2. I squared it. 4 minus 3. What the heck did I do wrong? Did I copy the equation wrong? No. Oh, stupid me. Pi over the cosine of pi over 6 is √3 over 2. So this would just be 3/4, and then this would be 3s across the board. 3, 3, 3, and then this would be yeah. So 4z. So this would be 3, 3, and then minus 1. Okay. Yeah, so that's the same thing. They just multiplied. If you multiply by 4/3, you get my answer, or something of that nature. Right? You multiply by 4, you'd get that. Okay, so yeah, that works. And then it would be a double-headed cone, but because they're restricting z to be greater than or equal to 0, it's just the top half of the cone. All right, let's see if there's any other ones that are worth kind of looking at. Rho, let's try this one. So rho equals 9 cosecant phi secant phi. So I don't know. So rho equals 9 times 1 all over sine phi times 1 over cosine. Is it theta? It's actually theta. Sorry about that. But if you multiply it back over, sine phi cosine theta is 9. This is the formula for x, so that's just x equal 9, which is a plane. Phi equals pi over 4 again. I mean, one way to think of the phi equals pi over 6 or phi equals pi over 4 is you're just letting this arm, the way that you usually talk about this, you're letting this angle be theta, and then you're letting this arm kind of rotate in space really quick. So if you did that, you would end up with that cone figure. Okay. Anyways, rho equals 4 secant theta. Or 4 secant phi. That's rho equals 4 times 1 all over cosine of phi. That's just going to give you z equals 4, so that's a plane. Okay, good enough. Yeah, so as you're going through, have your formulas, you know, this picture with the formulas there. So it's not, you know, it's not like a something you would program, like an algorithm or something. It's more, you're going to have to spin your wheels a little bit and kind of, you know, try this, try that, and then hopefully eliminate the rho theta phi and get it in terms of x, y, z, or vice versa. Okay, and then the same for our cylindrical equations. You want this little picture, and then you'll be able to go through it and do that. Okay, well, anyways, I think that's good enough. Thank you for watching, and we'll see you next time.